Benzene is a remarkably stable molecule due to its aromaticity. However, its dense cloud of pi electrons makes it an ideal target for electrophiles. Understanding how substituents change this reactivity is the key to mastering organic synthesis. In an EAS reaction, an electrophile replaces a hydrogen atom on the ring. This process involves a temporary loss of aromaticity as a carbocation intermediate forms, followed by the restoration of the double bond system. Not all benzene rings react at the same speed. Groups already attached to the ring can either donate electrons to speed up the reaction or withdraw them to slow it down. These are known as activating and deactivating groups. Substituents influence the ring through two paths: inductive effects through sigma bonds and resonance effects through pi systems. For many groups, like hydroxyls and amines, the resonance donation far outweighs the inductive withdrawal. When a second group is added, it can land in three distinct positions relative to the first. The existing group acts as a director, funneling the incoming electrophile to specific locations based on electronic stability. Activating groups, like the hydroxyl group in phenol, donate electron density into the ring via resonance. This increases the nucleophilicity of the ring, specifically at the ortho and para positions, making them highly reactive. By drawing resonance structures, we see that the negative charge resides on the ortho and para carbons. Because the electrophile is positively charged, it is naturally attracted to these electron-rich sites rather than the meta position. When an electrophile attacks the ortho position, the resulting carbocation can be stabilized by the lone pairs of the substituent. This fourth resonance structure provides extra stability, lowering the activation energy for the reaction. Conversely, deactivating groups like the nitro group pull electron density away from the ring. This makes the ring less nucleophilic and overall much slower to react with electrophiles compared to pure benzene. Resonance shows that deactivating groups place positive charges on the ortho and para positions. Since the electrophile is also positive, it is repelled from these sites, leaving the meta position as the least bad option for attack. Halogens are unique. They are deactivating because their high electronegativity pulls electrons away through sigma bonds, but they still direct orthos para because they can donate lone pairs through resonance to stabilize the intermediate. Let's look at toluene. The methyl group is weakly activating through hyperconjugation. When we nitrate toluene, we get a mixture of ortho and para products, with very little meta product formed. Now consider benzaldehyde. The carbonyl group is electron withdrawing. Because it destabilizes the carbocation at the ortho and para positions more severely, the bromine atom is directed to the meta position. Comparing reaction rates is vital. Phenol reacts millions of times faster than benzene, while nitrobenzene requires much harsher conditions, such as higher temperatures, just to react at a fraction of the speed. Size also matters. While a group might be ortho-para directing, a bulky substituent like a tert-butyl group will physically block the ortho positions, forcing the electrophile to the less crowded para position. To summarize, electron-donating groups activate the ring and direct orthos para. Electron-withdrawing groups deactivate the ring and direct meta. Halogens are the exception, being deactivating but orthos para directing. Quick question, based on what we've learned about resonance and electron withdrawal, where would a cyano group direct an incoming electrophile? Think about the stability of the ring. The cyano group is strongly electron withdrawing, making it a meta director. Mastering these patterns allows you to predict the outcome of complex chemical syntheses. Thank you for watching. Generated by Vision Solve AI.